Yes, good morning, students. In the previous class, I have explained electrostatics, means electric potential, electric fields and charges, electric potential and capacitance. Combinedly, we call it as the electrostatics. In that major part, it's completed yesterday. Then, first one, the charge Q is to be divided. I told it is actual, I think. Even I'll repeat it. A charge capital Q is there. A charge capital Q is there that is to be divided into two parts. This charge is to be divided in two parts, small q1 and small q2. Small q1 and small q2, we have to divide this. To get the maximum force between these two parts, between q1 and q2, if you want the maximum force if you want, for the maximum force, Q1 is equal to capital Q divided by 2 and Q2 is also equal to capital Q divided by 2. To get the maximum force between these two parts, Q1 will be Q by 2 and Q2 will be equal to capital Q divided by 2. And to get the minimum force between them, between Q1 and Q2, in between Q1 and Q2, we have to get the minimum force. Minimum force is equal to, whenever you take Q1 is equal to 1 coulomb and Q2 is equal to Q minus 1 coulomb. Q minus 1 coulomb. Like this, we have to divide this. We have to divide these charges. Q1 is 1 coulomb and Q2 is equal to Q minus 1 coulomb. Like this, we have to divide. Right? In CET, previous CET, they have asked it. A charge 2Q is divided into two parts, Q1 and Q2. This is divided into Q1 and Q2. To get the maximum force between them, what is the ratio of Q divided by Q1, they have asked. What is the ratio of Q1 divided by Q? It is asked in the previous CET. Then we know whenever we want for maximum force, how to divide it? For maximum force, Q1 is equal to Q2 is equal to Q divided by 2 general part. Here, what is the Q value? 2Q is there. That's why we'll write Q2Q. Q1 or Q2 is equal to 2Q divided by 2. Therefore, these two get cancelled. Then what it will be there? It will be equal to Q. That means Q1 is equal to Q2 is equal to Q. Therefore, ratio of Q divided by Q1. Q is Q only. Q1 is also Q only. So Q is equal to Q. Q1 also equal to Q. Then we will get 1. 1 is the answer for it. Okay? Like this. Next, linear charge density. Linear charge density, lambda. Charge per unit length is called as the linear charge density. Charge per unit length is called as the linear charge density. Its a unit is taken as coulomb per meter. This is coulomb per meter. Coulomb per meter. Coulomb per meter. First. Second one. This is a linear charge density. Surface charge density. This is surface, SURFAC. Surface charge density. Surface charge density. Sigma is equal to Q divided by A. Sigma is equal to Q by A. Its unit is taken as a coulomb per meter square. Coulomb per meter square. Third one, volume. Charge density. Volume charge density is equal to charge divided by unit volume. Its unit is a coulomb per meter cube. This is the volume charge. Okay. So then we come to that next one, electric potential. It is the amount of the work done in bringing a unit positive charge from infinite to a point in the field. It is the amount of the work done in bringing a unit positive charge from infinite to a point in the field is called as the electric potential. So electric potential is a vector quantity. It is electric potential is a vector quantity. It is away from the positive charge. Direction of the electric field intensity is away from the positive charge, and direction of the electric field intensity is towards the negative charge. So let us suppose electric potential at a point P, which is at a distance R from the charge Q. Electric potential at a point P, which is a distance small r. Then V is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught into Q divided by R. 1 by 4 pi epsilon naught into Q divided by R. This is the electric potential at a point P due to the charge Q. Then electric potential due to the negative charge at the point P is at a distance R from it. Then electric potential at a point P due to the negative charge. So V is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught into Q divided by R. R square won't be there, only R will be there. 1 by 4 pi epsilon naught into Q divided by R. Then electric potential due to system of charges. Whenever we take that, it's a equilateral triangle is there. At the corners of this equilateral triangle, charges are placed. A charge Q is placed here, a charge Q is placed here, a charge Q is placed here. These are the charges they have placed. Then the electric potential at the centroid of this triangle we require. Electric potential at the centroid of the triangle. This is at a distance of, centroid is at a distance of it is at a distance of A by root 3. Let us suppose its side is taken as a A or D, anything we can take. A, if I take side length is taken as A, then it will be equal to A by root 3. This will be A divided by square root of 3. A divided by square root of 3, that is the distance. Then the electric potential at the point, at the centroid, if you want, that will be electric potential at the centroid is equal to V1 plus V2 plus V2. The charges are placed at three corners, V1, V2, V3. Then the electric potential at the due to this, whenever we take V centroid is equal to 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught into Q divided by A by root 3. A by root 3 plus 1 by 4 pi epsilon naught into Q divided by A by root 3 plus 1 by 4 pi epsilon naught into Q divided by A by square root of 3. Like this we have taken. Then V at centroid is equal to Q divided by 4 pi epsilon naught, if I take common, root 3 divided by A plus square root of 3 divided by A. This A also we can take common. Okay, we'll take it. Square root of 3 divided by A. Therefore, electric potential at the centroid is 3 root 3 Q divided by 4 pi epsilon naught into A. 4 pi epsilon naught into A. Or we'll write this generally. V electric potential at the centroid is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught into 3 root 3 Q. 3 root 3 Q divided by A. Like this also you can write. This is the electric potential at the centroid. Instead of that, one of them are the negative charges. For example, this is the negative charge. At the point B, negative charge is there. Then we'll take it as the minus V2. This we have to take minus V2. This is minus V2. Minus V2. All of them will take that minus V2. It will be minus we have to take here. Therefore, minus 3 by 2, square root of 3 by 2, square root of 3 by 2 get cancelled. Then the electric potential at the centroid is equal to 1 by 4 pi epsilon naught is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught into Q divided by square root of 3Q divided by A. 1 by 4 pi epsilon naught into square root of 3Q divided by A. One by 4 pi epsilon naught into 3Q divided by A. This is the electric potential at the centroid. This is the electric potential at the centroid when the three charges are placed like this. Okay. For example, charges are placed at a distance 1 meter, 2 meters, 4 meter, 8 meter, like that. The resultant electric potential at the origin of the coordinate system, they'll ask it. So for infinite series, S infinite is equal to A divided by 1 minus R. This is the formula for the calculation of the infinite series, called as the geometric progress. This is called as GP, geometric progress. For infinite series, geometric progress. First term is taken as A. It is, let us suppose, 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. Like that, if they are, what is the first term? First term is taken as A. One is taken as a first term. First term is taken as A. First term is taken as A. First term is taken as A, and the second term is taken as R. Like this we will take, right? Charges, they are placed. This is a direct problem. Charges are placed at the x-axis. Charges are placed along the x-axis at distance, at the distances. At the horizon, what is the potential we have to calculate? When the charge Q is placed at 1 meter from the horizon, and a charge Q is placed at 2 meters from the horizon, and a charge Q is placed at 2 meters, and a charge Q is placed at 4 meters, and a charge Q is placed at 8 meters, like this. So whenever we take this on this, the resultant electric potential at the horizon we have to take. The resultant electric potential at the horizon, we have to say that. So what is that resultant electric potential? V is equal to V1 plus V2 plus V3. So V1 is equal to 1 by 4 pi epsilon naught into Q divided by 1 plus 1 by 4 pi epsilon naught into Q divided by 2. Like this we will write. So 1 by 4 pi epsilon naught into Q divided by 4 plus 1 by 4 pi epsilon naught into Q divided by 8 plus so on we will take. So on we will take. This is, so the electric potential V is equal to Q divided by Q divided by 4 pi epsilon naught into 1 plus 1 by 2 plus 1 by 4 plus so on, that we will take, plus so on we will take. So V is equal to Q by 4 pi epsilon naught 1 plus 1 by 2 plus 1 by 4, so on we will take. Then the resultant electric potential is to be calculated. This is taken as A, first term. This is taken as a second term, R. For geometric progress, and for the infinite series. Geometric progress will take that. A is equal to 1 and R is equal to 1 by 2. What is this? S infinite is equal to A divided by 1 minus R. Therefore, S infinite is equal to A is equal to 1 divided by 1 minus 1 by 2. So S infinite is equal. This is 1 divided by 1 by 2. 1 divided by 1 by 2. That it comes to numerator. That will be equal to 2. That will be equal to 2. S infinite is equal to 2. S infinite is equal to 2. We will take. Right. Then we will get that the resultant electric potential at the horizon V is equal to 2Q divided by 4 pi epsilon naught. 2Q divided by 4 pi epsilon naught. This is the electric potential at the point. So then we'll get that a neutral point, that's called as the zero potential point. Zero potential point is not possible for the system of the like charges. So zero potential point. Zero potential point. Zero potential point is not possible for the system of like charges. It is possible only system of unlike charges. So when the two charges Q and minus Q, they are separated, Q and minus Q, if they are separated, q1 minus q, if they are separated by certain distance, they are separated by certain distance, they are separated by certain distance, then zero potential point it may be formed anywhere. Let us suppose at this point zero potential point if it forms, which is at a distance x, and it is r minus x, like that we will take, or d minus x, we is to take that. It is taken as a d minus x if I take. Then position of the zero potential point from the neutral, from the charge of the, from the smaller charges, q2 is greater than q1, q2 is greater than q1, then x is equal to d divided by q2 by q1, q2 by q1 plus 1. If the zero potential point is formed between the charges, it will. So if the zero potential point is formed outside the system of charges, zero potential point if it forms outside the system of charges, zero potential point is outside system of charges. Why? This is the distance between them is taken as a t. So q1 and minus q2. Then zero potential point is a distance y is equal to d divided by q2 by q1 minus 1. q2 by q1 minus 1. This is the position of the zero potential point. Zero potential point is at a distance. Zero potential point is at a distance. Means outside the system of charges from the weaker charge. Here q2 is greater than q1. So then zero potential point due to an electric dipole, no, zero potential point not, electric potential at a point due to an electric dipole, due to an electric dipole V is equal to 1 by 4 pi epsilon naught into P cos theta divided by R. P cos theta divided by R square will be here. It's from derivation. R square, why did we get it? It's if you want to know, we have to go for derivation part. It is there for PU board level. Derivation part is there. So then V is equal to 1 by 4 pi epsilon naught into P cos theta divided by R square. If you take on the axial line, on the axial line, theta is taken as 0 degrees. Then the electric potential at a point on the axial line. Electric potential on the axial line is 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught into P by R square. P divided by R square. On the equatorial line. on the equatorial line. This is theta 0 on the equatorial line. Theta is equal to 90 degrees. Then V equatorial is equal to 0 because cos 90 becomes 0. Cos 90 becomes 0. Then equipotential surface. Next one is equipotential surface. The surface on which each and every point, if it is on the, if is each and every point, if it is at the same potential, the surface on which each and every point is at the same potential is called as the equipotential surface. Called as the equipotential surface. For example, that the charge is there, charge Q is there. From the charge equally, then electric field intensity will be there. Then potential on this, let us suppose this is the line it is taken. So potential on this point. So potential at this point, at this point, at this point, at this point, all the points potential will be same. This is called one equipotential surface. So another one, if I take that, the potential at this point on this potential here, anywhere, the potential, if you take that potential, is called as that equipotential surface. These are called as the equipotential surfaces. The electric field is directed like this. Let us suppose electric field is directed like this. These are equipotential surfaces. Whenever we take electric field is like this. This is the direction of the electric field. Then electric field intensity is taken as equal. This is one potential, one equipotential surface. This is taken as one equipotential surface. This is another equipotential surface. This is another equipotential. Here, at all these points, potential will be same. That is called as, at all these points as the potential is same. This is called as one equipotential surface. So on these points, all the points which are there, on all these points, potential will be same. This is also called as equipotential surface. So on this line also, each and every one is at the same potential. This is also called as the equipotential surface. Equipotential surface will say that. Each and every one is at the same potential. If we say that, equipotential surface. Okay. So electric potential we want on a charged spherical shell. Let us suppose it is a charged spherical shell of radius small r is taken. Charged spherical shell of the radius small r or capital R, anything we may take. If I take that radius of this one is capital R, radius of this one is taken as capital R. The electric potential at this point means on the surface is V is equal to 1 by 4 pi epsilon naught into the charge Q, it is there, Q divided by R, Q divided by R. Or this will be same either on the surface or inside here. Anyway, the electric potential V is equal to 1 by 4 pi epsilon naught into Q divided by R. How much potential is there on the surface? The same potential we observe throughout this. So same potential we observe throughout this. This is that equipotential surface. This is called as the equipotential surface, that will say that. Fine. This is called as equipotential surface. Next, We come to that capacitor. We come to that part, capacitor. Capacitor is a device to store the electric charge. Capacitor is the device to store the charge. The ability of the capacitor to store the charge is called as capacitance of the capacitor or capacitance of the capacitor. 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 The ability to store the charge is called as the capacity of the capacitor. The ability to store the charge is called capacity. That will say that capacity. The ability to store the charge is called as the capacity. Right. The charge stored in the capacitor. Let us suppose this is the capacitor. So if you want, how much charge will be stored in it? The charge stored in it, if you want, that depends upon the potential difference. Charge stored in the capacitor Q depends upon the potential difference between the plates of the capacitor. Then to replace this proportionality, we multiply with a constant where Q is equal to CV, where C is called as the capacitance of the capacitor. C is equal to Q divided by V. Q is equal to CV or C is equal to Q divided by V. Its unit is coulomb per volt we can write, but generally we use the unit as a farad. Farad is the larger unit. Generally microfarads they'll use. Microfarad. 1 microfarad is equal to 10 power minus 6 farad. Or they'll use that as picofarad. 1 picofarad is equal to 10 power minus, no, nanofarad. Nano. 1 nanofarad is equal to 10 power minus 9 farad. 1 picofarad. 1 picofarad is equal to 10 power minus 12 farads. Minus 12 farads. This is. So 1 picofarad is equal to 10 power minus 12 farads. This is 1 picofarad is equal to 10 power minus 12. Like this, we'll write capacitance of the capacitor is the ability of the capacitor to store that charge in it. The how much charge it can store in it is called as the capacitance of the capacitor. So then spherical capacitor, capacity of the spherical capacitor when we take capacitance of the spherical capacitor, if I take capacity of the spherical capacitor whenever we take capacity of the spherical capacitor whenever we take C is equal to 4 pi epsilon naught 4 pi epsilon naught into R. Capacitance of the spherical capacitor is C is equal to 4 pi epsilon naught into R. C is equal to 4 pi epsilon naught into R. Capacitance of the spherical capacitor. So capacitance of the spherical capacitor is independent on the charge, but it depends upon the size of the, it depends upon that, independent of the charge, it depends upon the size of the capacitor. So capacitance of the spherical capacitor is independent on the charge and it depends upon the size of the capacitor. So earth is considered as a sphere. Earth is considered as a sphere. Radius of the earth is taken as radius of the earth is taken as 6,400 kilometers. On substituting this value, what is this? capacitance of the spherical capacitor C is equal to 1 by 4 pi epsilon naught is equal to 9 into 10 power 9. But 4 pi epsilon naught is there. So that will be equal to 1 by 4 pi, sorry, 1 by 9 into 10 power 9. 1 by 9 into 10 power 9. This is the value of 4 pi epsilon naught. The value of 1 by 4 pi epsilon naught is equal to 9 into 10 power 9. This is a 4 pi epsilon naught is there. So 1 by 9 into 10 power 9. 1 by 9 into 10 power 9 into radius is taken as 6,400 kilometers. 6,400 kilometers. So I'm simplifying this. We'll get that C is identically equal to 711 microfarads. Practically, potential of the earth is considered as 0, then its capacitance will be infinite. As potential of the earth is taken as 0, its potential is taken as 0, then its capacity or capacitance of the earth is, the capacity or capacitance of the earth is called as taken as infinite. Capacity or capacitance is taken as infinite, right? So when the two spheres are taken, the big sphere whose radius is taken as smaller, capital R, and small spheres are there. These are the small spheres. So we split like this. We have split like this. Then radius of this one is taken as R. Radius of the big sphere is taken as a capital R. Radius of these small spheres are taken as small. So then volume of the big sphere is equal to, like n, we have split into n identical spheres. A big sphere of or big drop of radius capital R is split into n identical drops. It's a spherical shape. So the volume of the big drop will be equal to n into volume of the small drops. N into volume of the small drops that will take. So volume of the big drop will be equal to 4 by 3rd pi r cube is equal to n into 4 by 3rd pi into small r cube. N into 4 by 3rd for r cube. 4 by 3rd pi, 4 by 3rd pi, that will take. So then r cube is equal to n into r cube. Therefore, r is equal to n power 1 by 3 into r. R cube is equal to n power 1 by 3 into r. R is equal to n power 1 by 3. This is the relation between the radius of the big drop and radius of the small drops. Let us suppose two capacitors, they are separated. Two plates. Capacitors, they have different shapes. They are in different shapes. So how the capacitors will be there? In each and every device, these capacitors will be there. How the, actually I forget to keep this, how the capacitor will be there, I thought to keep it, but I forget. I am going to show you. Capacitors depends upon the requirement, different size they are making. Spherical capacitors are there, parallel plate capacitors are there, cylindrical capacitors are there, that will say. That will say, depends upon the requirement, they'll make a different shapes. So all these are the capacitors. See, all these are the capacitors. This is called as the cylindrical capacitor. These are that spherical means this spherical shaped capacitors. All these are capacitors. This is also capacitor. This is all these are capacitors only. All of them are called as capacitors. So this capacitor, another name is condenser. Condenser or capacitor, both will be same. For you may see for the fan, if you see that fan, one cylindrical body is there. That is called as condenser. Nothing but capacitor. What is the purpose of the capacitor? It stores the charge in it and supplies to the device. So first capacitor, it will store the charge in it, and it will supply to the device. That is the purpose of the capacitor. The ability of the capacitor to store the charge will say capacitance of the capacitor. Ability of the capacitor to store the charge will say that capacitance of the capacitor. So let us suppose two plates means what? Whenever we take that a capacitor consists of combination of the two plates, maybe spherical plates, maybe parallel plate, like that. So always a pair of the plates only can form the capacitor. Single plate, it cannot store the charge. Where that means energy will be stored. This is that these are the plates of the capacitor. In between these two plates, charge will be stored. So charge won't be stored on the plates of the capacitor. It will be stored in between the plates of the capacitor. So let us suppose two plates are separated. Let us suppose two plates are separated by a distance. This is one plate. This is one plate, and this is the other plate. Distance between the plates is taken as a d. Let us suppose these are the two plates. Each plate area is taken as a. A is the area of each plate. These two plates are separated by distance. Then the capacitance of the capacitor, C is equal to epsilon naught A divided by D. C is equal to epsilon naught A divided by D. C is equal to epsilon naught A divided by D. This is the capacitance of the spherical capacitor. C is equal to epsilon naught A divided by D. That will take. So A is the area of plates. D is the separation between the plates. Epsilon naught is called as the permittivity of the free space. For example, between the plates, a dielectric medium is introduced. First, there is no dielectric medium. Now, a dielectric medium of dielectric constant K is introduced between the plates of the capacitor. In between the plates, if a dielectric constant K is placed, a dielectric constant K is placed. K is the dielectric constant. Then with the dielectric medium, the capacitance of the capacitor will be K epsilon naught A divided by D. With the dielectric medium, the capacitance of the capacitor will be K epsilon naught A divided by D. K epsilon naught A divided by D. That is that capacitance of the capacitor. C medium is equal to K epsilon naught A divided by D. This is when a dielectric medium of dielectric constant K is placed, then new capacitance, the modified capacitance of the capacitor, C medium is equal to K into 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught into A. 1 by 4 pi epsilon naught 1 by K into 1 by K into epsilon naught A divided by D. K into epsilon naught A divided by D. Then medium, we'll write that capacitance of the capacitor in medium is equal to K into capacitance of the capacitor in air. We will take capacitance of the capacitor in medium is equal to K into capacitance of capacitor in air. We will take this is C medium is equal to K into air. C air, K into C air. Right, capacitance of the capacitor in medium is equal K times the capacitance of capacitor in means air. K times that of air. So let us suppose two plates, they have the different area of cross sections. Two plates have the different area of cross sections. Let us suppose this is the we'll take that. This is the two. These are the two capacitors I am taking. The two capacitors are like this. The two capacitors are taken like this. These are the two different areas they consist of. First plate area, A2 is the second plate area. They have formed that one capacitor. Separation between the plates is taken as a D. D is the separation between the plates. Then the capacitance of the capacitor. Capacitance of the capacitor we have to take with the smaller area only. Capacitance of the capacitor C is equal to epsilon naught A divided by A1 divided by D. Epsilon naught A1 divided by D we have to take. If this is A2 is small, then we have to write A2. If A1 is small, we write A1. C is equal to epsilon naught A1 by D. C is equal to epsilon naught A1 divided by D. So for example, two plates of the capacitor, they are connected with a wire. The wire for K is called as the dielectric constant. For air or vacuum, K is equal to 1. For air or vacuum, K is equal to 1. And for a medium, K is greater than 1. And for the metals, K is equal to infinite. K is equal to infinite for the metals. K is equal to infinite for the metals. That's why whenever these a capacitor, two plates of the capacitor are connected with a wire. The plates of the capacitor are connected with a wire. The plates of the capacitor are connected with a wire. These are connected with a wire. The plates of the capacitor are connected with a wire. The capacitance of the system will be infinite. This they have asked. These are direct problems. These two are direct problems. C is equal to epsilon naught A1 divided by D. If area of cross section. If the two wires, two plates of the capacitor are connected with a connecting wire, the capacitance becomes infinite. As potential between the plates becomes zero. After connecting, what happens? They'll reach to that potential. Potential between, they'll be neutralized. Whenever they are connected with the wire, they'll be neutralized. So the potential will be zero. If potential is zero, capacitance will be infinite, because Q is equal to CV, then C is equal to Q divided by V. Q divided by V. So something by zero will be equal to infinite. That's why the capacitance of this capacitor will be infinite. So instead of that, they used to ask, N plates are there, alternative plates, they are connected like that. They'll say these are the plates. These are different plates are there. These are the different plates. When the alternate plates are connected, then the number of capacitors we have to take. Number of the capacitors we have to take. These are the alternative plates, they are connected. Then this will form one capacitor. This will form capacitors C3, C4, C5, C6, C7. How many are there? Total 7 capacitors are there. Total 7 capacitors. Number of the plates when we take, how many number of plates are there? 1, 2, 3, 4, 5, 6, 7, 8. Number of plates are is equal to 8. But number of capacitors, how many? 7. Number of capacitors are 7. Number of capacitors are taken as 7. That means we'll take that. If an identical plates are connected, means an identical plates alternately they are connected to form the capacitors. So then the capacitance of the means number of capacitors will be equal to n minus, or capacitance will be equal to n minus 1 into C. N minus 1 into C. The new capacitance of the combination will be equal to n minus 1 into C. N capacitors they are connected, means n plates are connected alternatively. Then the number of capacitors will be equal to n minus 1. So the new capacitance of this system, the effective capacitance system will be equal to n minus 1 into C. The effective capacitance of system will be equal to n minus 1 into C. N minus 1 into C. That we will take. Next. Capacitors, we may connect in parallel, we may connect in series. Let us suppose series combination of the capacitors. Series combination of the capacitors. When 3 capacitors of capacitance C1, C2, C3, they are connected to a battery, positive and negative terminals, positive and negative terminals. This will be C1, C2, C3. So in this, same charge will flow, charge flows. So potential difference V1, V2. V is equal to V1 plus V2 plus V3. In this, the potential difference is V1 plus V2 plus V3. The total. Then effective capacitance in the series combination will be equal to 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 divided by C3. 1 by C1 plus 1 by C2 plus 1 by C3, like this. 1 by C1 plus 1 by C2 plus 1 by C3. 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3, like this. This is the pattern. If you want to calculate the potential, V1 or potential V2, potential V3, shortcut formula is, so V is equal to 1 by C1 divided by 1 by C1 plus 1 by C2 plus 1 by C3 into V. So 1 by C1 plus 1 by C2, 1 plus 1 by C3 into V. Like for anyone we may write V2 is equal to 1 by C2 divided by 1 by C1 plus 1 by C2 plus 1 by C3 into V. V3 is equal to 1 by C3 into 1 by C1 plus 1 by C2 plus 1 by C3 into V. Like this we may write. This is a series combination of the capacitors. So for n identical capacitors, n identical capacitors, if they are connected in series, effective capacitance will be equal to C divided by n. N identical capacitors, each of capacitance is taken as C. then the effective capacitance of the system is, then this is recuably. Please mute. Recuably. Okay, CS, when unidentical resistors they are connected in series, an identical capacitor they are connected in series, effective capacitance of system will be equal to C divided by N. Okay, we will solve one problem here. We'll solve the problem here. Potential across C1, C2, C3 are taken given. Then let us suppose this is 1 microfarad, 1 microfarad, 2 microfarad, and 3 microfarads. C1 is equal to 1 microfarad, C2 is equal to 2 microfarads, and C3 is equal to 3 microfarads. Then the effective capacitance 1 by CS is equal to 1 by 1, 1 by 1 plus 1 by 2 plus 1 by 3. Therefore, 1 by CS is equal to, if I take 6 LCM, 6 LCM, if I take 6 plus 3 plus 2, 1 by CS is equal to 11 divided by 6. Therefore, CS is equal to 6 divided by 11. 6 divided by 11, 0.54 like that. This will be equal to 0.54 microfarad. Microfarad. N identical capacitors, they are connected in series. For example, the capacitors are connected like this. The capacitors, they are connected like this. How many are there? Let us suppose each one is 4 microfarad, 4 microfarad. Okay, 6 microfarad. Let us suppose each one is this is 8 microfarad. I am taking 8 microfarad, 8 microfarad, 8 microfarad like that. 8 microfarad is there. What is the effective capacitance of this system? Effective capacitance, they are in series. CS is equal to C divided by A. What is that individual capacitance? 8 microfarads. Like how many are there? There are N is equal to 4. 4 capacitors are there. Therefore, CS is equal to, C means what? 8 divided by 4. 8 by 4 means what? 2. So 2 microfarads. Like for N identical capacitors, we'll write like this. Then parallel combination of the capacitors. When the capacitors are connected in parallel, effective capacitance will be calculated, and in series combination, same charge that flows, but in parallel combination, charge will split. In series combination, charge is constant. In parallel combination, potential difference is constant. So for this, a battery is connected, battery of V volts, it is connected. That will take that C1. C2, C3, they are connected like this. Potential. Charge, look, we have tried. Then charge that splits into Q1, Q2, Q3 like this. Q1, Q2, Q3 like this. The charge it splits. Then the total charge Q is equal to Q1 plus Q2 plus Q3 total charge. Then we'll take that. Capacitance of the effective capacitance in the parallel combination is Cp is equal to C1 plus C2 plus C3. Cp is equal to C1 plus C2 plus C3 like this. So effective capacitance. Let us suppose this is 3 microfarads, 3 microfarads, 3 microfarads, 6 microfarads, and 9 microfarads like this. This is Cp is equal to, what is that? Cp is equal to C1, 3, 6 plus 9. So Cp is equal to 9 plus 9, 18 microfarads. Is 18 microfarads it is effective capacitance. $18 microfarads that will take. Okay. Then if you want, what is the charge that is passing through C1, C2, C3 individually if you want? Charge Q is equal to C1 divided by Q1 is equal to C1 divided by C1 plus C2 plus C3. C1 plus C2 plus C3 into total charge Q1. So if you want to charge Q2, Q2 is equal to C2 divided by C1 plus C2 plus, this is not G, this is C. Will be equal to C1 plus C2 plus C3. Like this will get. Q2 is equal to C2 divided by C1 plus C2 plus C3. This is okay. Then n identical capacitors are connected. If n identical capacitors, for n identical capacitors, the effective capacitance of that for n identical capacitors in parallel combination. When n identical capacitors are connected in parallel, the effective capacitance of the system Cp is equal to n into C. The effective capacitance of the system will be equal to Cp is equal to n into C. If n identical capacitors are connected in parallel, effective capacitance of system Cp is equal to n into C. Okay. Now we'll do that. Two capacitors are taken. Actually, one capacitor only. So it is that one plate of the capacitor. This is the other plate of the capacitor. In between these two dielectric mediums are introduced. Between the plates, two dielectric mediums are introduced. Dielectric mediums of thickness d by 2 and d by 2 they have placed in between these two. Then these are same. These are same thickness are there. Area will be same. It will be like this. Let us suppose in between the two plates, a dielectric medium of dielectric constant K1 is introduced. In between that in between these two, dielectric constant of K2 is introduced. So area of each capacitor. Earlier, it is only one capacitor. In between the plates of the capacitor, two dielectric mediums they are placed, K1 and K2. So this is that C1 is the capacitance of the capacitor. C2 is the capacitance of the capacitor. So these two they latch. D is the distance between the two plates. But what happens? It is a d by 2. It is taken as d by 2. It is also taken as d by 2 and d by 2 like this. D by 2 and d by 2 like this. So then D by 2 and D by 2. So C1, C2 are the two capacitors. C1, C2 are the capacitors. There D by 2 and D by 2 it is taken. Then these two are considered as a series combination. How to say that series combination? First end, second end, first end, second end. If the capacitors are taken first plate to second plate and first plate to second plate, like that, if the capacitors they are connected end to end, if the capacitors are connected end to end, like end to end, if they are connected, then this combination will say that series combination. This is called as the series combination. So then we affect two capacitance of this one is CS is equal to 2K1 K2 divided by K1 plus K2 into C. CS is equal to 2K1 K2 divided by K1 plus K2. 2K1 K2 divided by K1 plus K2 into C. This is the effective capacitance of the system. Instead of that, two capacitors are there, means two plates of the capacitor are there, and this in between the two plates, in between the plates, the electric mediums of dielectric constants K1 and K2 they have introduced. Let us suppose this is a one plate, this is a dielectric constant, this is a one plate, this is half. Okay, next one more is taken. This in between the two plates, dielectric mediums are introduced. These are the two plates. In between the plates, a dielectric medium is introduced. Let us suppose two capacitors of capacitance. These two act dielectric constants K1 and K2 they are introduced. So this will act as a capacitor of capacitance C1. This will act as a capacitor of capacitance C2. Then what about this? This is for the first plate A by 2. For the second plate A by 2 is there. Distance is same for the two plates. Then the effective capacitance of this CP it is. What is that? This combination will say that parallel combination. That is first end. This is the first end, second end. First end, second end. So first ends if they are connected to one terminal, and second ends if they are connected to other terminal, such combination is called as the parallel combination. Such combination will say that parallel combination. So CP is equal to K1 plus K2 divided by 2 into C. CP is equal to K1 plus K2 divided by 2 into C. So effective capacitance CP is equal to K1 plus K2 divided by 2 into C. This is the effective capacitance of the. This is the effective capacitance of the effective capacitance of system, right? This is the effective capacitance of the system, right? CP is equal to K1 plus K2 divided by 2. K1 plus K2 divided by 2 into C. This is the effective capacitance of the system in terms of the dielectric constants, right? This is energy stored in the capacitor. Whenever work is done to store the charge in it, when the charge is stored in it, to store the charge, energy will be needed. Energy stored in the capacitor. Energy stored in the capacitor. U is equal to half CV square. U is equal to half CV square, half QV, or U is equal to half Q square divided by V. That we'll check it. Third one, we'll check it. Then how to it? So Q is equal to CV. Q is equal to CV. If I substitute this one, Q is equal to CV. If I substitute this one, then Q is equal to CV. Q is equal to CV. Q is P is equal to V proportional. Q is equal to CV. Q is equal to CV. Then V is equal to Q divided by C. V is equal to Q. Okay, so Q is equal to CV. From this, V is equal to Q by C. I'm substituting this. U is equal to 1 by 2 into Q into V is equal to Q divided by C. So U is equal to half Q square divided by C. This is the third equation. This is the third equation. U is equal to half Q square divided by C. This is right. Energy stored in the capacitor is. Let us suppose the plates of the capacitors, if they are connected like this, when the two plates of the capacitor are there, when these are the two plates, C1, C2, that will take positive plate, negative plate, positive plate and negative plate. These are connected like this. Then we'll take that common potential after connecting potential across this V1, potential across this V2, common potential C1 V1 plus C2 V2 divided by C1 plus C2. C1 V1 plus C2 V2 divided by C1 plus C2. This is a common potential. So loss of energy delta U is equal to half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. This is V1 minus V2 whole square. Next. Plates are taken like this, two capacitors. These are the two capacitors. This is taken as C1. This is taken as C2. Okay, positive plate, negative plate, negative plate and a positive plate. They are connected like this. Potential across is V1 and V2 like this. Then the common potential V is equal to C1 V1 minus C2 V2. So C1 V1 minus C2 V2 divided by C1 plus C2. C1 plus C2. So loss of energy, if I take that 1 by 2, delta E is equal to 1 by 2. C1 C2 divided by C1 plus C2 into V1 plus V2 whole square. into V1 plus V2 whole square. This is that capacitance means loss of energy. This is related to that electric potentials, right? We'll solve that in numericals. Okay. We'll solve the numericals tomorrow. I didn't keep the numericals, and just time is there. We are going for that other chapter. We didn't complete that these logic gates. We did complete the logic gates. I'll explain the logic gates now. Logic gates. Logic gates, there are AND gate, OR gate, NOT gate. Combinedly, AND gate and NOT gate, NAND gate, we call that NAND gate. Combinedly, this OR gate and NOT gate is called as the NOR gate. These are the gates. So we have discussed AND gate, OR gate, NOT gate, NAND gate, NOR gate. First one is these gates, they works on the Boolean algebra. 0 and 1 only will be there for the Boolean algebra. Okay, we will see this. It may not be completed now. We'll see tomorrow. Right, I'm going to stop the class here. Thank you.
Thank you, sir.
Thanks, sir.